So for test 3, we covered, for this test, we covered basically two things. We covered exponentials and logarithms. On the sheet that I gave you there, let's start out with logarithms. Basics of knowing logarithms is knowing the definition. And in the definition of logarithms, we have a conversion from logarithms to exponentials. And so that's 1A, I'm asking you there. Convert this logarithm to exponential form. And so how does a logarithm work? Well, of course, we know that in our logarithm form there, the base, what base do I have? I have base 3. And so when I convert that to exponential form, that is the base of my exponential form, isn't it? Now what goes on the exponent of that base 3? Yeah, this number right here is the exponent, and then equals then the stuff in the parentheses there. What I'm taking the logarithm of, that's what that equals. So yeah, it's a conversion from one form to the other, and of course vice versa. This exponential form also goes back to log form. So that's the way it works. The base, of course, is the base of the exponent, and then the y over here is the actual exponent, and then that equals 5x. So we'll have to do something like that. Now, on B, this is the same thing, because if I say evaluate using the definition of logarithms, if possible, what I mean by that is the very same thing. The definition of this is the definition of logarithms. This goes to this, and that goes to that. That's the definition of logarithms. So if I say use the definition of logarithms, that's what I mean. All right. So let's see if we can do that the way I did it in class anyway. As I said, well, this is going to be equal to something. Call it question mark, whatever you want to call it. And so convert that to exponential form. We would have what? We'd have 6 to what power is 1 over 1296. And then you're just looking for the power of 6 that happens to be. Now, that power of 6, the 1296, is maybe one you're not that familiar with, but just go through the powers of 6. You know, 6 to the third is 216. 6 squared is 36, but 6 to the third is 216, so it's not that. And then if you go to 6 to the fourth, what do you get? 1296. Okay, so we know it's tied in with 1296, the fourth power anyway, but it's 1 over 1296. So how would I get 1 over 1296? Make it a negative, yeah. So the power here, 6 to the minus 4, gives me 1 over 1296. Yeah, if you've got the power and you need to flip it over, just make it a minus power. So that means this logarithm is negative 4. Log base 6 is 1 over 1296 is negative 4. Okay? Now, a couple of things about logarithms. On the same thing on number or letter C, what does that one equal to? Well, I'll have, if I convert that to exponential form, it'd be 9 to what power is negative 729. Well, true enough that 9 to the third is 729. That is true. But what about negative 729? Well, if I try negative 3, does that work? No, because that's 1 over 729, not negative 729. How do I get a negative 729 out of the power of 9? You can't do it. Okay. Yeah, this is not possible. It's not a real number. And the thing we remember there is why one of the other ways we could have seen up front, what do we know about what we take the logs of? This number in here can't be what? Can't be a negative or 0. It can be anything else, It just can't be a negative, and it can't be 0. So inside the log, you can't be a negative or 0. And it's because you can't get a power of that base to equal a negative number or 0, okay? As far as a real number goes. All right? Now, on D there, I can't very well use the definition of logarithms. You see why? Because if I use the definition of logarithm, I'd be saying 5 to what power is 600. That would be by definition, right, of logarithms. And is there a power of 5 that gives you 600? No. 5 to the 4th gives you 625. 5 to the 3rd is 125. So there's not a power, a nice power of 5 that gives you 600. So that's why here I'm saying let's use this change of base theorem. And on the change of base theorem, what I'm referring to there is if you have any logarithm whatsoever, logarithm base A of B, the change of base theorem says you can change it to any base you want, but to help us out, change it to natural log or common log, either one, but we can change this over to common log by doing what? Doing the natural log of B over the natural log of A. In other words, what you're taking the log of on top and then the base, the natural log of it on the bottom. So in this case, what is this logarithm equal by the change of base? By the change of base theorem there, what do we have? Well, it would be the natural log of what over natural log of what? It would be the natural log of 600 divided by natural log of 5, wouldn't it? And that will allow us to figure out this logarithm, even though it's not a nice power of 5, because we can do natural logarithms on the calculator. 600, divide that by ln of 5. I get 3.97. And how many ever places they want there, I didn't specify, but I probably will on the test. But if it doesn't, a couple of places will be fine. Okay? All right. Is that okay? Any questions or concerns on question number 1? All right. What about number 2? Well, number 2, again, keeping on the theme here of logarithms, there are properties of logarithms. Matter of fact, we did 3 of them, and maybe could add a couple more to that, but the 3 basics, you know, if you've got 2 logarithms added together, you can combine them, subtracted, you know, those properties are what I'm referring to there. Won't write them all out here now, but you can go back and refer to those. So that's what I mean on 2A. Let's use those properties of logarithms to expand on A, that logarithm. All right, so what do we know about expanding that? Well, I can expand, if I look at this as two things divided, this divided by that, I can expand that into 2, and what's the operation if I expand those into 2? It'd be log base 8 of 10x cubed, what? Log base 8 of the square root. Minus, yeah. In that case, if I have 2 things divided, it turns into subtraction. So it would be 10x cubed log base 8 minus log base 8 of the square root of y minus 7. Okay, but I can do some more, because what about this right here? Don't I have a times 10 times x cubed? And if I have 10 times x cubed in my logarithm, I can expand that into 2 logarithms, log base 8 of 10 plus log base 8 of x cubed. And then keep the log base 8 of the... Well, now the other thing to mention, because of what we want to do here next, let's also write, instead of square root of y minus 7, how can I write the square root as a power? 1/2 power. Yeah, the square root can be written as the 1/2 power, and that'll help us to expand this a little bit further, because what is the last thing then? So that's the first one we did, that was property 2 of logarithms. The second thing we did there was property 1 of logarithms. Property 3 of logarithms, what can we do now? These powers, what happens? Put them in the front. Yep, and that's why we did that to that one. Yeah, the powers can be written in front. So we have log base 8 of 10 plus 3 log base 8 of x minus a half log base 8 of y minus 7. And one other note on that, that's it. That's the answer. Because I can't expand a minus and I can't expand a plus. So inside, if I've got a minus or plus, I can't expand. So I can't expand this y minus 7 any further. Okay? Now going the other way is condensing. And yeah, like I said, it's just the reverse of it. One thing we can see on 2b there to condense is, well, if expanding we bring the powers out, condensing means we need to take the numbers in. So these numbers in the front of my logarithms, when I'm condensing, those need to go inside. And where do they go on the inside? Well, they become the powers of the things on the inside. So it'd be log base 4 of x cubed minus parentheses log base 4 of m to the 5th plus log base 4 of y. Y squared, I should say. Okay, and so next of all then, as we typically do, we go left to right unless parentheses. So we do parentheses first. Putting the parentheses here together, well, we've got a logarithm plus a logarithm. Those can be condensed into one logarithm, like we were saying before. We don't add the stuff on the inside. It multiplies, yeah. When we're condensing logarithms, if we've got them added, they condense, but you multiply the insides together. So it'll be m to the 5th times y squared on the inside of the one log base 4. All right, well, that leaves us what? That leaves us a minus 2 logarithms subtracted, and those can be condensed into 1 log base 4. However, you don't subtract the insides. What do? You divide. So it'd be x to the 3rd divided by m to the 5th y squared. So 1 logarithm is that right there. Okay? All right, another thing we did a lot of is we did solve several types of equations. Problem number 3 has 2 examples of exponential equations. Now, exponential equations are exponential equations because you have the variable and the exponent. So if I have variables in the exponents, I've got two processes I can possibly do. 3a is the first one we talked about, and that is when we have the same base on both sides. If you have the same base on both sides of your exponential equation, you can cancel the bases out. Now, I don't exactly have the same base on both sides, but I do have a 9, and I can write that as base 3, can't I? And so that's what I'm going to do here. I'm going to write 9 as base 3, and 9 as base 3 is 3 squared. Okay, and so now I do have the same base, and the only thing of note there is what do I do with these? I've got 3 squared, and then I have that to the x minus 5. Don't I have to multiply those? So this is really over here 3 to the 2x minus 10, because I have to multiply that 2 times both of those. So what happens? Base 3's cancel. Really nice. And so I get x minus 7 equals 2x minus 10. Yeah, it's just a nice little equation there. Get the x's on one side, the constants on the other. Doesn't matter. I'm going to go this way. I'm going to subtract x. That's the easier way to go, and add 10. And so that gets me 3 equals x, doesn't it? X's cancel, 10's cancel. Right? So those are really nice if you got them. Same base on both sides. Or can you make the same base on both sides? Now we're on 3b. I can't do that. Well, first of all, you see what I'm going to first of all have to do on 3b? I need to move the 8 over, yeah. So first of all, let's move the 8 over. So I've got plus 8, 3 to the 5x equals 208. Yeah, and 208 is not a nice power of 3, so I have to do something a little different here. And what do I do on these type here if I can't get the same base on both sides? Well, that technique is ln both sides, isn't it? Take the ln of both sides, because what can I do then if I do that? Well, I can bring the 5x out. So it'd be 5x ln of 3 equals ln of 208. Now I just have 5 times x ln of 3. So all I have to do is get rid of the 5 and the ln of 3, which all I have to do is divide by the 5 and the ln of 3. Wouldn't that get rid of those? 5's cancel and the ln of 3's cancel. So yeah, that would get me x equals. And so then just punch that up and see what it is. ln of 208 divided by, and again, one more time, if you're putting it all in at once, be sure to, since I've got two things on the bottom, be sure to put parentheses around it. So that'd be 5 ln of 3 in the bottom. So that'd be 0.9716. Again, I didn't say how much to round off, but I probably will try to do that on the test, but it's about 0.97 to 2 decimal places. Okay? Question or concern? All right, number 4. Well, number 4, we're getting into the log equations, which we do those a little bit differently. What do you see, first of all, needing to happen on number 4, though? Well, just like on number 3b, I need to get this logarithm by itself, so I need to move the 4. And all I'd have to do there is minus it both sides. Minus the 4 both sides and get the log base 7 of x minus 1 equals 5. Now it's set up with how we solve these log equations. Remember how we did that? That we called exponentiate both sides to whatever base your logarithm is. In this case, it's base 7. And so I exponentiate both sides to base 7, which brings up another property of logarithms that we talked about. And that property is, well, that what happens in this such a case. If I have 7 to the log base 7, that cancels out, doesn't it? And so I have 8x minus 1 equals 7 to the 5th, which is a pretty big number, but it is just a number, 16,807. So now it's just a matter of solve for x. So add 1, both sides. So 8x equals 16,808. And divide by 8. And x equals, let's see, that reduces by 4, doesn't it? Huh? Oh, reduced by 8. Yeah, it does. Hey, how about that? 2101? Okay. They won't all come out nicely like that, but this one did. All right? Oh, I circled that one, but what else do we have to be careful with on these answers we get for logs? Be sure this works inside the logarithm, right? Because we know that the logarithm can't be the log of a negative or a 0. But that doesn't look like it's any problem. If I plug in 2101 right there, that's going to be okay, because that's going to be definitely the logarithm of a positive number. That's what we're saying. Just check to make sure you don't get the log of a negative or 0 with those. All right, number 5. Same idea. It's a log equation. So I need to exponentiate both sides. However, the exponentiate both sides only works if you have one logarithm on the side. Well, in this case, I've got 2 logarithms on the left. I need to make that into one logarithm, don't I? And so we just talked about that. To combine these into one logarithm, well, they're 2 logarithms added together, so I would do what to the insides? Multiply, wouldn't I? So this 2 logarithms on the left becomes 1 logarithm by multiplying the inside. So that would be the log base 3 of x squared minus 24x, because I wouldn't have to distribute the x there. Now we can exponentiate both sides. I've got base 3, so I'm going to exponentiate both sides to base 3, because then the base 3 and the log cancel out. On the left side, so I have x squared minus 24x equals 81. Well, we might run into a quadratic equation, and one such as this, I would make one side 0 and factor, hopefully. Yeah, subtract the 81. And so I would have x squared minus 24x minus 81 equals 0. And that does factor pretty nicely. It's 27 and 3, isn't it? 27 and 3 is 81. To make it a minus 24, I need a minus 27, but a plus 3. So check me on that. Does that sound right? Does that look okay? All right, so then set those each individually to 0. Add the 27, so we get x equals 27. Subtract the 3, so we have x equals negative 3. However, only one of those works. I have to reject this one, don't I? Why? Can't take the log of a negative. Yeah, if I plug in x to be negative 3, that gives me the log of a negative number in both cases. All right. 27 doesn't have such a problem. Okay? All right, a couple more on this little review I'm doing. Any question on that one? Okay on that one? All right. Yeah. One other thing I wanted to review with you was the graphing part of our discussion. We graphed exponentials and we graphed logarithms. And on this one, I want to graph 4 to the minus x minus 12. Well, we had two types of this is an exponential one. The exponent has the variable. We had two types of exponential graphs. We had the decreasing and we had the increasing variety, and just kind of the hockey sticks. And just kind of review which one is which. How do I know, just going in, which one I have? This if the exponent is, if you have the negative exponent here, a to the minus x type here, and this is if you have a to the positive x, the base being a, some number. Yeah, if you have a minus exponent, it's this type, and if you have a now this one, I do have a minus exponent, don't I? So I'm expecting the decreasing downward. Okay. So that helps me. Now, what else is of note here? Well, I've got this minus 12. And by shifting, what does that tell me? That's going to be shifted down 12 units, because on these, and that specifically tells me something about my asymptote, because if I don't have any shifting, my asymptote is at 0. If I shift it 12 down, that's going to put the asymptote where? Negative 12. Yeah, so my horizontal asymptote is no longer at 0. It's 12 down, so that would be y equals negative 12 is my horizontal asymptote. So let me go ahead and draw that in. So at negative 12, somewhere along about there, I am expecting this horizontal asymptote, which just means it levels off. And on this case, one on the it's going to level off. Should level off on the right side. Okay, but I do the way we did it is, yeah, we just did a little table, 5 values, and if it's not shifted right or left, you can just usually get by with negative 2 to positive 2, something like that. If it's shifted right or left, shift it accordingly. but negative 2 to positive 2 is okay. All right, so we just plug those in for x. If x is negative 2, what have I got? Well, that's going to make a positive 2, actually. 4 to the positive 2, which is 16, minus 12, which is 4. Whoop. Negative 2 meant positive 4. At negative 1, about the same thing, isn't it? 4 to the minus 1 is 4 to the positive 1, which is positive 4. Then you minus 12, you got negative 8. So at negative 1, I'm at negative 8. At 0, what about, that'd be 4 to the minus 0, which is just 4 to the 0. What about 4 to the 0? That's 1, isn't it? So I have 1 minus 12, that's negative 11. At 0, I'm at negative 11. 1, see 4 to the minus 1, minus 12. Well, remembering that a negative power flips it over, that's going to be 1 over 4 to the positive 1, or 1/4, minus 12. So that's going to be, well, it's negative 11 3/4, or negative 11.75. And then last but not least, when x is negative 2, let's do that one over here. For the negative 2 minus 12 would be 1 over 4 squared minus 12, which is 1/16. So that'd be negative 11 15/16, I do believe, or something equivalent. All right? So putting those on here, negative 2, 4. See, this is going by 5s, right? So it'll be 4 right there. Negative 1, negative 8. Long about in there. 0, negative 11. Right about there. 1 and, hey, where'd you come from? Okay. All right. 1 is negative 11 3/4. 2 is negative 11 15/16. Yeah, so we've got some pretty good points there. We've got these here, but yeah, it looks like our hockey stick was prediction was right there, something like that. All right. So what about the logs? Well, the logs. The thing about the logs is when I'm graphing them, I do have a vertical asymptote, and if it's not shifted, it's at 0. So the vertical asymptote is x equals 0, right here at the axis. Y-axis it is. Okay. Points-wise, well, if you have base 3, I would choose base 3 numbers over here. Powers of 3. Which can start with 1, 3 to the first, 3 to the second, 3 to the third. Those will be some good ones. Just powers of 3. Because when you do your logarithm then, you got log base 3 of 1. Well, that means 3 to what power is 1? That would be 0. 0 power. Log base 3 of 3. Plug in x to be 3. 3 to what power is 3? That's 1 power. Plug in x to be 9, you have log base 3 of 9. 3 to what power is 9? That'd be 2. So 9y is 2. And then log base 3 of 27. 3 to what power is 27? That would be power 3. So yeah, you get this this right here, 1 0 3 1. 3 right there. 9 2 27 3. Yeah, so you get this